Hi, welcome to the iolite automation webinar. Today we'll be taking you through iolite's automation features to help you improve your data processing. My name is Spence Paul, I'm the iolite manager, and joining me will be Joe Petrus, and the two of us make up the iolite team. Just as an overview of what we'll be covering today, we'll start off with an introduction to automation in data processing, and then we'll be looking at iolite's processing templates. What is a processing template and what do we aim to do with them? We will be creating a simple example looking at trace element spot analyses. Even though we're looking at spot analyses, the same can be applied to imaging experiments. And then once we've created an example template, we'll also look into some more advanced examples. We won't have as much time to cover them in detail because they are more complex, but more just sort of give you a feel for what is out there and what is available. And we'll finish up with a summary, and we'll have time for some questions and a discussion at the end. Just to let you know, we won't be covering the Python API in detail in this presentation. It's too large and it'll be the subject of its own webinar. And we do assume that you're familiar with the basics of iolite. If you aren't, then we recommend seeing the previous webinars. Also, there is this example dataset that you can download from this link here, and it has the data that we'll be using today so you can follow along, but it also has some example templates that you can use as a taking off point to build your own. So feel free to download those and follow along. Just as an introduction, iolite has had processing templates for ages, so but we don't get a lot of questions about it, which suggests to me that there's not that many people using it because normally if there's a lot of people using it, we get a lot of questions. But so we started thinking about it in 2014. It was a conversation I had with someone who said, you know, I do the same thing over and over. Why do I have to keep clicking the same buttons over and over? And I was like, okay, all right, maybe we could do some sort of templating system. So it's been around for a long time. We released it, it was first released in early 2015. The ideas behind it are just as relevant now as they were when we put it out. In fact, perhaps even more so now that laser ablation is becoming more routine and common. So obviously, one of the major reasons to automate things is for time savings. It is much, much faster. Especially once you get it set up for your lab, it is much quicker. And that initial time investment that you spend setting it up is recouped very quickly. One of the most important parts is the additional reproducibility. So sometimes it does make a difference if one person always crops off 2 seconds at the start and one person only crops off 1 second at the start of every ablation. Sometimes that can actually make a difference. And we actually have seen data sets where that's the case. It gives that reproducibility and then that confidence that if everyone's following the same recipe, that you'll get roughly the same results. Even those people who love to do things manually will have to admit that they sometimes make mistakes, myself included, with clicking buttons and typing really fast. In fact, I make heaps of errors typing really fast. Even if you think you're a fast clicker, you make more mistakes than automation will. Also, you can build these processing templates up to be quite complex and to look at more than one thing at once. So humans have trouble processing more than about 3 different variables at once because we can think in 2 dimensions and then maybe 3 dimensions. But then as soon as we start getting, trying to work out 4-dimensional type things and the relationships between those, we start to have trouble. Whereas a computer can do that very easily. So as soon as you start putting in criteria for more than 3 or 4 channels, the computer's potentially going to do a better job than you. Like I said, you can keep them very basic if that's what you feel comfortable with, or you can make them super advanced if you know what you're doing and you're happy to check the results of that. And they can do all sorts of things. And possibly the most powerful thing that we have is the ability to call Python scripts, which then opens up a huge amount of potential for getting data from other places and sending data to other places. We want to assure you that you do retain full control. So you can still run QAQC checks, you can still pause the template execution, you can still fully review what has happened, and we'll show that in the examples as well. We absolutely want to avoid a black box type scenario. iolite's very keen to never leave people in the dark about what's happened during the data processing workflow. So I just wanted to bring this up at the start, that there's always this balance between automation, which gives you speed and reproducibility. So, you know, in an ideal world, we just run a script and we just get numbers at the end. But the problem with that is it doesn't take into account the variability that you might have within your samples. And so that's where you need some, on the flip side, you need some human oversight and some intervention. Sometimes you're going to need to adjust your selections. Sometimes you're going to need to throw samples away or some data away. And that comes from our understanding and our insight about the processes that are happening that the automated system doesn't have. So it's always this balance between doing things super fast and super reproducibility, with super reproducibility, and having this ability to inspect things and to make sure that it's doing what you want it to do. So just to keep that in mind, we will show a whole bunch of automation, but how far you take that is up to you. So just to illustrate where processing templates can have the most effect, this is just a typical workflow that we've sort of sketched out. So you might start off with some data import, where you import your mass spec data and a laser log file. Then you'll create some selections. Then you might calculate some results running in DRS, etc. Then you probably want to perform some QAQC, make sure that your secondary reference materials have performed the way you expect them to. Then you would potentially then go back and adjust your selections. You then might look at whether the data makes sense. You might make additional plots, those sorts of things. And then once you're happy with it, then you'd export your data. In this process, these parts here involve a lot of repetitive actions. So creating selections can be done faster using processing templates. You can also use it, as I said, with algorithms, running DRSs, performing QAQC, this data import sort of stuff. This is all the sort of thing that is takes up a lot of clicks, but is prime for automation. But we do reserve this area here, this detailed analysis, for the operator. So this is the part that we're not necessarily saying it should be automated. Okay, so I've been talking a lot about processing templates, but I haven't actually explained what one is yet. So what is a processing template? Well, basically, it's just a series of actions that are performed in order. A little bit like a macro, if you think of it that way, or like a recipe. And an action in iolite can do a bunch of things. It can be importing your data, it can be calculating results, those sorts of things. And once you have a template set up, the inputs to that template are normally the files that you want to load. And so when you open a template, you just change which files you want to point it at, or which files you want to be opened, and then you run your processing template. So once you have a setup for your lab, you then only need to change those parts, the paths. And as we'll see today, there'll probably be a bunch of times where when you're experimenting with the processing template, the best way to do it is to just experiment, is just get in there and start putting in actions. The worst thing that it can do is that it'll create a session file that's rubbish. You just close it and start a new session. So don't be afraid to experiment. iolite never changes your input data, so it'll never change the data you got from your mass spec. So you can just keep rerunning processing templates on it. And so this is just a list of the current actions that are available. There's a few others that we're thinking about adding, but if there's anything that you think that could be an action, feel free to contact us as well. And as I mentioned, probably the ultimate level of automation is to run Python code. We'll only do a quick example of that at the end today. So let's have a look at the processing template view. So when you look at the iolite window, there's these series of icons down the left-hand side here. And at the very top there, normally we start in the data view, but if you click on the templates view up here, that'll show you the processing templates view. And what we have here is along the top, we have some buttons for loading and saving templates. Once you've loaded or saved a template, you'll be able to see its name down the bottom here and whether or not it's been modified. And then here we have the list of actions that make up that template. So initially your template will be blank, but then once you add a bunch of actions, they'll appear here. You can add and remove actions using these buttons up here. You can also rename an action using this little button that looks like a pencil drawing on paper. And you can copy an action. So that's really handy, that one, if you're doing a lot of repetitive steps. Then when you click on an action in the list, it will show over here on the right-hand side, the current action settings. So the settings depend on what type of action it is. Some have very few settings and some have quite a few settings, depending on how you set it up. But this is where you change the settings for a particular action. And then once you're happy with your template, you can click the Run button up here, and it will run through each of these steps, starting from the top, moving down to the bottom. So we'll do an example. This is going to be using the Gabbros dataset, which is a trace element spot analysis experiment. It's the same one that we used in the basics webinar. So if you've seen that webinar, hopefully it's familiar. In this experiment, we did measure some NIST, some BCR2, and some BHVO2G. The basalt glasses were our secondary reference materials. We also were measuring a set of 4 different minerals. And if you're not a geologist or a geoscientist, it doesn't matter what those minerals are. Basically, just think of them as different types of sample within this sample. So actually, if you look here on the right-hand side, you can see an image of what the rock looks like. So the opaques are these really dark-looking grains. The plage are these lighter ones. And the olivines and the CPEX are in there as well. And I'm going to point out that even though this is a spot analysis, and all the examples today will be looking at spot analyses, I just wanted to mention that the processing templates can equally be applied to imaging experiments and are regularly. It's just that their imaging templates tend to be quite short. So you just do possibly the first 2/3 of what we're going to do today. So you create your selections, or you input your data, create your selections, and then run a DRS, check your results, and then look at the images. So just before we start making this together, I thought I'd list what goals we want our template to do. So we want it to automatically load our data, create some basic selections so that we can run our DRS. Then we want to run the DRS using imported internal standard values. And then we want to check our secondary reference materials using a QAQC module. And then we would, at that point, we would normally go and look at our selections, check them, make sure they make sense. And then we want to export our results. So that's what we're going to try and do today in our example, is create a processing template that'll do that. So let's start a quick demo of that. Oh, actually, just before we do, I have to make mention of timestamps. We use a couple of different files in this. They're both Agilent files from our lab. The first one has this sort of date stamp, which is the first in the list, I believe, and you need to define that. Otherwise, you'll get some issues with that. So I'll just switch over. Can everybody see? Oh, actually, just before we go, I've actually got this this template ready to go. This is one that I prepared earlier, you could say. You have a copy of this in your folder. And if you click Run, you can see that it imports the data, creates all our selections, imports the internal standard values, runs the DRS, and then we'll run the QAQC. And now it's waiting for us to say that it's okay to continue and to export our results. So that probably took maybe, what, a couple of seconds, maybe 3 seconds. And I don't think there's anyone who can click with their mouse fast enough to beat that. So that's just to give you a demo of what we're going to try and do. Okay, so let's start a new session. and we're just going to change our timestamp. So if I click and hold on the import file button here in the data view, and I'm just going to change it here to this first one, day, month, year, hour, minute, second. And so that's now set for this experiment, so it should be fine. And now if we go up here and we click on this templates action, you should see this here, which is the template view with no template loaded. So let's start by adding an action to import our data. So we're going to click this add button, and we're going to say import instrument data. And we're going to call this action import MS data. Click OK. And you can see now we have this action in our list, and you can see over here that it's giving us our options. And at the top here of the settings, so now we can see the settings for that action, you can click on this and it'll allow us to set whether or not we want to import a single file or a whole folder of files. In this case, in our Gabro's example, we have just a single file from an Agilent. And then here, it's asking us for the path to that file. So where is the file that we want to load? And we can specify that by clicking the button here. And we're going to be loading in the example data folder. There's a Gabro's example folder. And the mass spec data is in the Gabro_data.csv file. The Gabro_log.csv is the laser log file. We'll be loading that in just a sec. And the Gabro_is_values.txt file is the internal standards file. But we're going to be clicking on this Gabro_data.csv file. This is our Agilent file. I'm going to click open. And that then tells iolite, or tells the template which file we want to load. This machine name, you can just leave that. That's for if you're doing split stream experiments and you're loading data from two instruments of the same type and you want to give them individual names. Now we want to load our laser log data. So we're going to add another action, and we're going to, sorry if I did that too quickly, we're going to click on this import laser log data action here, and we're going to call this import laser log. Now, you don't have to have a laser log file. It just makes it much easier to create selections if you do have one. We'll be showing an example later on of if you don't have one, how to get around that. So there's some options up here for the path to the laser log file. Now, if we click on this, you can either get it to prompt you when the template runs, and it'll ask you to select the file, or you can use the specified file, which is like what we did for the mass spec data, or you can say, look in the import folder, and it will look in the folder where it loaded the mass spec data, and it'll be expecting a file with the exact same name, except that it has log in it. We could do that here in this example because they do have the same name, but just to show you how it works, we're going to click on this use specified file, and then we're going to specify that file. So we're going to, in the path, we're going to click this ... button. We'll go to the Gabro's example file and the Gabro_log.csv again. So that's our log file there, the Gabro_log.csv. Now, obviously there's always an offset between your laser log file and your mass spec file. And there's a couple of ways that iolite can deal with that. If you have already run experiments with this setup and you know the offset, you can actually just type the offset in here, or you can do an auto sync. That doesn't always work, but if it doesn't work, you can always do it manually and then type in the offset. But in this case, the auto sync will work well for us, and 99% of cases it does work for you. And what we can do at this stage is we can save our template, and I'm going to call this my template. It has the file extension .tpl, that just stands for template. It doesn't mean anything. The actual file itself is just a text file. If you open it up in a text editor, you can see
that it just has each action and the settings for it. So I'm going to replace that one. And what we can do now, like I said, when you're making your own templates, you can just try them out and just run them over and over again until you find the settings that you like. So in this case, we're just going to run it. And you can see that it imported the file, we got a tick, and we imported the laser log, and we got a tick as well. And if we go to the data browser now, you can see that we have our Gabbro data mass spec file that's loaded, and we have our Gabbro log file that it's loaded as well. And if we were to go to time series, we'd also see that we have our data. So that's a good start. So just to recap, we had our import action where we told it what file we want to load. And then we had our laser log file. Same thing, we told it what log file we want to load and how we want to sync the two. So now we have a list of samples that are recorded in our laser log file that we can start putting into our selections. So we can break them up into selection groups, and that'll allow us to run our DRS. There's 3 options for making selections at the most basic level. The 3 options are from our mass spec samples, or from our laser log samples, and from channel data. I'm going to come back to channel data later on, but the difference between from mass spec samples and from laser log samples is that when we look at our mass spec files, so this is an example here where we have where the mass spec is measuring, it measures some background, then the laser switches on, we get some data, and then the laser switches off, we have a little bit of washout. That's what it would look like if you had a separate mass spec file for each analysis. But if you have your lab set up like ours, sometimes the one mass spec file will have hundreds of spots in it. So if you do use mass spec samples, you do need to allow for this wash-in time, or if there is any wash-in time and any wash-out time. In comparison, laser log samples are actually much simpler in that they just record when the laser switches on here, and they record when the laser switches off. So if we create a selection from this, it's just going to occur between here and here. Whereas if we create a selection from this particular mass spec sample, it would include the baselines and the washout time until we started cropping in from the edges. The cool thing about laser log samples also is that you can actually move backward from the start time. So I'm just going to try and draw this in. So if we move back, if we put in a start crop of minus 20 seconds, we could go back, say here, and this is minus 20 seconds, excuse my drawing with the mouse, and we could say we want our selection to go for 18 seconds, so it would go from there to there, and then we've used this laser on period to actually select baseline, so select this period here. And we'll do that in just a sec. So that's just one way of using the laser log file. Even though it records when the laser's on, we can still use it to select baselines. First. So in iolite, the way that these 2 different samples are arranged are that mass spec samples. So if I'm in the data browser view and I click on the samples tab up here, the mass spec samples are in the top half of the window, and laser log samples are in the bottom half of the window. And if we go back to our experiment that we're working on, if we look at that, you can see that we have just a single mass spec sample because everything was combined into one file and it's an Agilent file. And we have all these laser log samples down here. So we're going to use laser log samples in this example, but you can use mass spec samples as well. So we're going to use the create selections action, and it has up the top here, it has this selector for the different methods. So that gives you those 3 choices that I talked about, from mass spec samples, from laser log samples, or from channel data. In this case, we're using from laser log samples. And then here we tell it what the destination group's name is. So the selections that you make are going to go into a group. What do you want to call that group? In this case, we're going to call it baselines. And if we're making a baseline group, we need to check this little checkbox over here. And that's because we could call this anything. We could call it baselines, we could call it baseline, we could call it backgrounds, we could call it BL. Doesn't matter what you call it, as long as you check this button over here so that iolite knows that this is a baselines group. Then here we have our crop options. So like I said, in this case, we're going to go back 20 seconds from when the laser switched on, and we want our selection to have a duration of 18 seconds. Below that, we have some options for what sort of spline we want to use. I like the step forward one as my default until I've looked at my data properly, because I think it works well for baselines, but it really depends on your instrument and what masses you're measuring. And then under that, we have this existing option. So if there are already selections in this group, and there might be, because this action might be anywhere in our template, what do we do with the selections that are created? Quite often you'll just want to replace the selections that are already there. But if you don't, there's an option to append them to the selections that are already there. And then underneath that, we have this match text box here and a couple of little buttons here. So the first button here, this little dot and a star, is the regex option, the regular expressions option. And when we click that, it's going to treat the texted here like a regular expression. And this one here means that when we check that, turn it on, it will look for this text in the entire path of the file. So to explain that a little bit better, what is a regular expression? So regular expressions are just a way of dealing with text as if they're patterns. So for example, if we wanted to select both NIST 610 and NIST 612 samples, we don't have to type out both of them. We can actually just type in NIST and then 6.1 because they both have that text in them. And then we can create this little, in these square brackets, we can give it some options. So after that, it can either be followed by a 0 or a 2. And that's just an example of a simple regular expression that matches both NIST 610 and NIST 612. Another example is if we would type in BCR2G and then _R, because in our experiment we'd put in run 1, run 2, run 3, run 4, etc. We don't have to type in all of those options. We can put in /D, which is regular expression code for digit. So it's just saying that there will be a digit, and the plus means that there could be one or more digits. So this means that it'll match BCR2G _ run 1 or run 09 or run 145, because all of these have the same starting pattern and then a digit, and it could be one or more digits. We don't have a lot of time to cover all of regular expressions. If you do want to know a bit more about it, and you don't have to use regular expressions, but if you do want to learn more about it, there's plenty of websites. If you type in regular expression helper into Google, this is the first one that came up for me, but there's plenty of resources out there. The other little tip that I'll bring up is that if you use an asterisk, that's shorthand for saying select everything. That just means match everything. And we'll use that in just a sec. You can also use this pipe symbol. So this is just the vertical line. For me, that's just above my enter key. And it creates an OR. So if I was to type in BCR/BHVO, that would match anything that had BCR or BHVO in it. So that's a way of selecting more than one type. It's an alternation. And finally, just on this matching text thing, you can also put in an exclamation mark at the start to basically invert your selection. So that is, it will select anything that doesn't match the following text. So if I typed in exclamation mark NIST 612, it would actually then select anything that doesn't have NIST 612 in its name. So I will just show how that's used by creating another action. So let's add an action, and we're going to create selections. So we're going to click on this create selections action, and we're going to call this one select baselines. And I'll just point out that I'm going to do this template the long way, slightly longer way, just so that you can see all the different steps. And then at the end, I'll show you that there's a way to automate quite a lot of this. But there are some issues with automating things, and I'll show you how to fix those as well. So let's do it the slightly longer way, and we're going to create this action called select baselines. Up the top here, I'm going to say from laser log samples, and then I'm going to say this is our baselines BLs group. So I'm going to check this button here, and I want to crop back 20 seconds, as I mentioned, and I want the selection to go for 18 seconds. I'm going to do that step forward option because I know that works for this particular data set. If there were any selections already in this group, I want to replace them because sometimes you'll rerun your templates. And as I mentioned, if we want to create selections based on all our samples, which in this case I do, I want to put a baseline before every one of my samples. I'm going to put in a star here. And that will then create baselines for us. So I'm just going to quickly run that just so you can see what happens. So I'm going to right click on this and say, run this action. You can see we've got a little tick to say that it worked. And if I go to the time series tab now, you can see that we have a baselines group. It's using the step forward, and you can see that we have all our little selections in here. Now, I'm going to save the template. Because I've done that, because I've run the template, if I try to run it again, it's going to complain because it's going to say, hey, you've already loaded this. So I'm actually going to create a new session. So once I saved my template, I'm going to say new session. So this is just because I'm running it as I go. You wouldn't normally have to do this. And okay, so we've selected baselines. Now we're going to select our standards. So we're going to create, add another action, create selections action. And this time we're going to select NIST 612. See why I like automation, because I'm a very accurate typer. So I'm going to click on this from laser log sample again as my option. And this time my destination group is going to be our G underscore NIST 612 because we want this to be our standard group. I'm going to crop off 1 second from the start and from the end, just to make sure we don't have any wash-in effects. And the spline type for this one, I'm just going to say spline and auto smooth. Again, I want to replace any selections that are there. And here in the match text, this is where I type in NIST 612 so that it selects only the NIST 612 samples. And that's my new action that will select our NIST 612s. And we're going to do the same thing with BCR2 and BHVO. Instead of having to do that all over again, what I'm going to do is I'm just going to copy the action. So I'm going to select it in our list, and I'm going to click this button up here on the far right that says copy the currently selected action. So I'm going to do that, and I'm going to call this one select BCR. So now we have a new action, and I'm going to change this one to say select G, to put the selections into G underscore BCR2G group. Everything else is exactly the same except for the match text. I'm going to type in there BCR. And then we're going to repeat that for BHVO. Like I said, this is the long way of doing it, but I think it illustrates what the automatic way does. So we're going to put this one into G underscore BHVO2G. Everything else is the same except for the text there. Okay, and now we're going to select our samples. So the way that we're going to do that, so we're going to say select samps, is we're going to put all of our, so in this example we had plagioclase, olivine, CPX and opaque analyses. We're going to put them all in the one group just to start off for this example. So we're going to call that group samps. Doesn't matter what we call it really. Same thing, we're going to crop off 1 second from the start and the end. This one, because it's a group of unknowns, we don't want any spline for it because the spline doesn't make sense when you're talking about individual samples. So we're going to leave that as no data. We're going to replace again. And in here, instead of trying to type in plage or opaque or whatever, I'm going to type in this negation thing. So I'm going to say anything that doesn't have NIST in it. I'm just going to check this button here because when I ran this demonstration the other day, I forgot to do that. So we're going to do a regular expression here. So I'm going to check that button. You can see it goes red. So we're going to do anything that's not NIST. And I'm going to use the OR button. So this OR symbol, which is the pipe symbol. I'm going to say OR BCR. Oops. And there for typing. BCR or BHVO. This is all case sensitive because it's very specific in how it selects it. And that will then select all of our plages, CPX, whatever. Okay, so that will select all of our baselines, our reference materials, and our samples. So I'm going to save that, and I'm actually going to run that template again just to see if it worked. So we'll click on the run button up the top here, and you can see it's already run. And when I click on the time series and look at, say, silicon, you can see we've got our baselines. Okay, that's worked out. We've got our BCRs, we've got our BHVOs, we've got our NIST 612s, and now we've got all of our, oh, no, we don't have samples. What have I done wrong there? So I've done it from the mass spec sample up here. And remember our mass spec sample, we've only got one mass spec sample. So it's created a selection that goes from the start of our data to the end of our data. So lucky I checked. If we go back to templates and we just change this to from laser log sample. If I'd actually copied one of those, it would have worked better. Okay, so I'm going to rerun this. And you can see now it's selected all of our samples properly. Okay, so that's creating samples the basic way. One thing that I didn't mention was this paths option. And the reason we put this in is because when I do some of my imaging experiments, sometimes the way that the people I just get the data and someone else has measured it, the way they set it up is that they have their standards in one folder, their standard analysis, and each scan line is in its own mass spec file. And they'll put all the standards in a folder called standards_1. Then they'll put the next sample, all the scan lines in another folder, and the standards, the following standards in standards2, and so on and so forth. But in that case, each of the samples has the same name. So there'll be like line 1 in standards, and there'll be line 1 in sample 1, and so on. So doing a search for line 1 will actually bring me up some standards, and it'll bring me up some sample. So if I check that little button, the path button, it will actually search the whole path for matches. So I can actually type in standards_1 to select my standards from this folder, and then I can type in sample_1 to select samples from here. So just so you know, that's an option as well. It does make the most sense for mass spec samples because laser log samples all come from the one file. Someone asked about loading laser log files, and do they have to have _log.csv in their name? No, they don't. That's why in that action, you can specify the name of any file. It's only if you choose this look in import folder option that it will ignore this and just look where it imported the mass spec data from. Otherwise, if you use this use specified file option, it'll load whatever file you tell it is here. I'm not sure if I understood how you import the mass spec data when instead of one file, your mass spec produces several separate files. So in that case, you would, instead of saying file, you would say folder, and you'd tell it what folder to look in. And when you do that, you tell it the folder location, and iolite will look through all the files in that folder and try to load anything that it finds in there. So if you have other files in there, like image files or whatever, it will ignore those and it'll only load the files it can. So now we want to import our internal standard values for our DRS calculations. So there is a few options for this. We can either load a file containing sample labels and the internal standard values that we've measured some other way, like say on the probe or something. And that would look something like this. The arrows here just represent tabs. So you can see the tabs. So you have the first column is the header has to be SAMP name. And then after that, you have whatever elements that you've measured, and you can have as many as you like. And then down this first column here, you have your sample labels, which should be the same as your selection labels. And then you have your calcium values and your titanium values or whatever. That's the best way to match up individual, say, probe analyses with your laser analyses. You can also set a single value for the entire session. So if, for example, you were analyzing just zircons for the entire session, you could set perhaps the silicon value to be 29%, something like that. I can't remember off the top of my head. Or you can set a single value for a particular selection group. So if everything in that selection group has the same internal standard concentration, then you can just set one value for that. If you do, and we'll do this later, if you do spread out your unknowns across multiple groups, when you run this from file option, you can use this all unknowns option for it, so it'll look in all your unknown groups to try and find matches. So that would look like, if we were to add to this here, if we click on add, and we're going to run this load internal standard values option here, and we're going to call it load IS vals. And the method up here, this is where we choose what we want to do. We're going to use the from file option, and then we're going to specify what file to load. So we click on this ... part, and we're going to click on this Gabbro_IS_values .text file that was in the Gabbro's example folder. And when you click on that, if you can see a little preview, you can see that it looks just like I mentioned, it's just tab delimited text file. Then here in this part here, we have to tell it what channel we want to use as our internal standard channel. In this case, just for this example, we're going to use calcium 43. Now you do have to tell it which mass of the element that you're using. We only have one calcium mass, but we still have to type in calcium 43, not just calcium. Then in the selection groups, you can just use this all unknowns, or if you only want to match up a particular group, you could actually select a group from here. But we're going to use this all unknowns. Here's the default value. So if it can't find a match in the internal standard values file for your particular selection, if their labels don't match, this is the value that it will use. The default value here is 1, but you could set it to be something like 10,000 so that you could find any that haven't got a match, and then you could correct those if you wanted to. And of course, what units our internal standard values are in. This little checkbox here just says, after you've finished loading this file, also pull out the calcium values, in this case, from our reference material files and put them and use those as well. So this is how we load our internal standard values so that each individual file is going to be corrected to its calcium value in this case. And now at this point, we're ready to run our DRS. So we're going to add an action and so we're going to say run data reduction scheme. And we're going to call it run trace elements. The names don't really matter. It's only for so that you can keep track of what each step's doing. And then here in our options, when we click on this, it'll list whatever DRSs that we have. I've probably got more than you have because we've got some experimental ones here. But in this case, we're going to select the trace elements DRS. And that then brings up the settings for it. So not all of the DRSs you might have might not all work in a processing template. They do have to have a processing template setting widgets function for those of you who are writing your own DRSs. So in this here, on this top left-hand side, we've got whether or not we want to use internal standards. We've loaded them, so yes. If you're perhaps running an imaging experiment and you just want to run in semi-quant mode, which is where you don't use an internal standard element, then you could just check this. Note that if you are going to use internal standards, you do have to have loaded them before you get to this step. So this action has to come before this action so that it's got the internal standard values there to use when it runs. Over on this top right-hand side, it's talking about what reference materials you want to use for which channels. Now, quite often you'll just use one reference material. In this case, we're going to use NIST 612 to correct everything, but we could add in here an option to say, I want to look at titanium 49, and I want you to use BCR2G for that. So you do have the option there of using different reference materials for different channels. In this case here, we're just going to use NIST 612 for everything. Then everything else in here is the same as the DRS tab here. You can put in detection limits. I'm actually going to leave them off just for this example because it'll run just slightly quicker because it doesn't have to calculate those. So that's importing standards. Just making sure I haven't forgotten anything. Okay, so after, actually I'll just run this just so you can see what happens. So if you right click on an action, you can select to just run that particular action. So I'm going to run the load IS values and I'm going to run the trace elements. And it should give you a nice little tick there. And then if we went to our time series tab, we should now have our intermediate channels and our output channels. So that's great. It's run its DRS. We now actually have results. If we went to the results tab, you will get this message because it's run in a template. You can just click no. And now we have results for BCR, BHBO, and our samples. And we can see those for our output channels. But we want our templates to be even smarter. We want it to automatically check our results and tell us if we should be worried about anything that's happened so far. And we can do that using a QAQC module action. So in this example, we're going to run a secondary check. So up the top here, when we add a QAQC action, you can choose which module you want to run. And this secondary check looks at your secondary reference materials and checks what values you got. You can have it so that, this little option here, this treat warnings as errors. If your QAQC module reports that some value was too far off from the accepted value, you can use that to halt the processing template. It'll actually stop at that point. It won't bother doing any of the following steps, and it'll alert you that your results aren't good enough. And you can set here also that it automatically saves the results from running this. So it will save the plot and the table as a HTML file, and you can tell it where you want to save those. Then you can set underneath that the settings for your particular QAQC module. In this example here, we are getting it to look at the results for BCR2G. And we're saying that anything that's greater than 10% from the accepted value is an alarm. And anything that's greater than 8% is just a warning. And if our group varies by more than 10% RSD for any channel, then that's an alarm. And if it varies more than 7%, then that's just a warning. I'm going to do a little quick spoiler here. Our iron values in this example were terrible. And so we're actually going to put in an exception. And I'll actually show you how to do that. So in our template, when we click add, we're going to add a new action. We're going to add this run QAQC module action towards the bottom here. And we're going to say check BCR 2G. And that's going to add this QAQC action. And I'm going to select this secondary check option here. I'm not going to treat warnings as errors because we are going to get warnings, but it will still tell us that something wasn't quite right. I'm going to tell it here that we want to look at the BCR2G results. And I'm going to just reduce those down again. I'm going to say 10%, and what are the values? I'm putting in 8% and 10% and 7%. And I already know that iron's going to come out at like 35% off the accepted value. And a bit of that is to do with using NIST 612 for measuring basaltic samples. It's not what we normally do. But the way that we do that, the way that we add an exception is if we double click in this table here, and it'll add an exception. So we tell it what channel we want an exception for. So I'm going to type in here FE57 score ppm. That's the channel that we know is going to be off. And we're going to say we don't even want a warning unless it's more than, say, 35% away from the accepted value. And it's not an alarm until it's more than 40% off. I know those numbers are ridiculous, but that's just in this example. And I'm going to say 30 and 40 for the warnings on RSDs. There. Okay, and now if we run that action, you can see that it gives us a warning because when we look at our table, our iron is 35% too low. So the accepted value is 96,000 ppm, and we got our measured value is 63,000. So it's down by a third of what it should be. So it's given us a warning. It's given us this little thing here. Like I said, we could choose to ignore that if we know that we got a channel that's consistently off. And we could have also saved this little plot here that shows how far off our average value. So this is looking at the average value for our BCR runs, where that plots relative to the accepted value. So that's the internal standard. Oh, so there's a quick question that said, can you run QAQC on multiple elements and also on multiple secondary standards? You can't do it on multiple secondary standards. If we wanted to check BHVO as well, we'd just add another action, add another QAQC action. And someone said they can't run them by right-clicking on it. That would be, you just need to update to the latest version. That's only been in for the last week or so. Okay, so now we've checked our results, and at this is the point where we'd want to actually then manually go and look at our results, and before it saves any results. And so what we can do there is we can put in a pause action. So in iolite, if we click add and click pause template execution, and we'll just call that pause to check. What will happen then is that when you run this template for real from the start, it'll do all these steps, and then it'll get up to this step, and then you can use, while it's paused here, to go and look at your results. You can then go and look at your time series in more detail. You can adjust your selections and those sorts of things. And then if we had, say, an export option after this, then we could click on resume and your template would resume. So it's a way of putting in breaks in your template so that you can check how it's going. And then finally, in this example, we're going to put in an export results action. So just like when you're exporting results normally, you've got a few different options. You can export to a file, and up the top here we have this method selector, so how you want to choose how you want to export your results. If we select file, which is probably the one that most people use, we can tell it where we want to save the file to. Whoops. And then the rest of that is pretty much the same as when you export normally. If you have some favorites, you can actually use one of your favorites. So we'll click add and say export data, and we'll call this export results. And if we had a favorite here, we could use that favorite. If we have a file, we could set it up here. So I'm just going to set up a really basic one. I'm going to say save this to my Gabbros example folder, and I'm going to call it export test one. Yep. And I'm going to I want my stats. I want an Excel format. I'm going to export anything that's a unknown or a reference material. I'm not going to export my baselines, and I'm going to export all my outputs. And just quickly, I'll just want a mean, 2 standard errors, and if we had LODs, we'd put them in here. Okay, so that's our a very basic processing template. So it does everything from importing data, creating selections, and exporting results. So I'm just going to create a new session that doesn't have any data loaded and doesn't have any selections in it, so that we can run it from scratch. So I'm going to click load my template, and then when we click run, it didn't like running. Because I changed that before when I was talking. So I'll just click save and run again. And now it's asking me to check my results. And once I'm happy with them, I click resume, and it's exported our results. So that is a basic way to create QAQC, a basic way to create processing templates. So now let's have a look at some more slightly advanced automation ideas. So as I mentioned, there's a few advanced ideas that we can cover in this. So one that we can do is to use multi-element selection criteria, or even single element criteria. We can also look at different ways of setting up your experiments so that you only check the results that you need to. You can create your own channels. You can perform optimization. So there's the ones that we'll look at today, but there's plenty of other things as well. So let's look at creating selections automatically. So one way we can do that is based on channel data, which I hadn't discussed it before. So let's look at the processing template _2, which is in that folder. I don't want to change that. There's this one here, Gabbros proc template _2. When I click on that, when we look at this select baselines option, all the rest are the same. What it's done here is it's not using from mass spec sample or from laser log sample, it's using from channel data. And it's selecting baselines again, but instead of doing it from the laser log samples, it's doing it based on channel data. So in this case, we've actually, I'm going to create this from scratch just so you can see what it looks like. So if I click add, create selections, I'm going to say select baselines, and I'll pop it up here. You can drag and drop your actions. And I'm going to say from channel data, so that when I say that, it opens up this extra thing here so we can put in our criteria. I'm going to say this is baselines, and you don't have to follow along with this one. I'm just going to do it quickly. I'm going to say crop off 1 second from the matches and from the end. The spline type is going to be step forward again. We're going to replace. And then here, what we're going to say is we're going to add a criterion. And we're going to say where total beam is less than 1 million counts, 1e to the 6 counts. And if I just run these quick actions here, just so you can see what our data look like. I think I loaded that twice. Anyway, when I look at our data, I'm going to look at it in the tools and automatic selections from channels view. So this is what this from channel data does basically. So if we were to look at our data and we were to zoom in on total beam and have a look at what our minimum values are, so what's between the samples here, you can see that basically nothing, so nothing is below 500,000 counts for a start. But it looks like most of our gaps between our samples are less than 1 million. So that's where I got that number from in my template. So if I say if total beam is less than 1 million counts, add it to our baselines. Sometimes we want to make sure that there's not just little tiny little gaps that get selected as well. So we can put in a minimum duration. So I'm going to say it has to be less than 1 million counts for 10 seconds at least. And I'm going to say it can be up to 1,000 seconds long. And if I run that action, what you'll be able to see is that we now have oh, I forgot to create a new session, but no biggie. So we have our baselines action. So this is the one that I just created from the samples. And the way that I can tell that it's not created from the laser log samples is that it's selected these data here at the end, because this is a match for where it's below. So that's another way of creating selections. This is just a simple case where I have done it based on the baselines, but you can also do this to avoid spikes for inclusions or for drill throughs or for those sorts of things. So, so we'll have a look at that again in just a sec. Before that, I did say I'd show you what happens when we'd go full auto with this. And I'll give you a spoiler alert. There's a few problems with it, and I'll explain those as well. Okay, so I'm going to click on load. I'm not going to worry about saving that one. And we have this processing template called Gabros _proc template _ full auto .template. When I click on that and load that, oh, actually, sorry, before I do it, I'm going to create a new session because I've already loaded data and created selections in there. Good thing about templates is it doesn't take long to get back to where you were. So I'm going to load that template that was had full auto at the end of it. Click OK. And you can see that it basically does the same as the previous examples, except that creating selections is done all in a single action here. And this action behaves quite similarly to this auto selections button here, in that it will try and group your selections according to how closely their names are similar, and it'll apply a trim. And you can also apply the automatic baselines. So in this case, it'll move backwards from the start of every selection 10 seconds and make one for 8 seconds. So let's just quickly run that so you can see what happens. I'm going to put in a pause action just so it doesn't run for as long, just after the create selections part here. No. Okay, so we're loading this and it's imported the data and it's creating selections. So when we go to our time series tab and we look at, that's a terrible color, but when we look at silicon again, you can see that it's created a baseline action, great. Sorry, baseline group, it's selected our BCR2s, it's selected our NIS 610s. Wait, hold on a sec. We didn't measure NIS 610. So that's your first red flag there. And we can go to our selections browser and say, what's going on in this 610? And when we look at that, we can see that it's actually a NIST 612 underscore run 10. And that was enough of a match that it mistakenly thought it was a NIST 610 run. But we can fix that easily just by dragging and dropping that into NIST 610, sorry, NIST 612. And then just to tidy that up, we'll delete that group with no selections in it. And so now when we go back to our groups, so we've got our baselines, our BCRs, NIST 610, BHVO, well, we can see that it's not splined. And that's because it didn't think that BHVO was a reference material, but we can fix that just by right-clicking on it and saying group type is reference material, telling it it's actually G underscore BHVO2G. We could have fixed that by, in our laser log file, or when we set up our sample, the way to fix that is if we called it fully underscore G underscore BHVO2G. Because we chopped off the 2G and the G underscore, it didn't treat it as didn't recognize it as a reference material. So that's how you can get around that. Excuse me. And then everything else has been put into the correct groups. So I just wanted to show that you can do it in a single action, but if you do that, you just need to be aware that your labeling needs to be a lot more precise. So now let's talk a little bit about avoiding anomalies automatically. We've got some synthetic data that we've created here, and it's in the folder. So we'll open a session file. So session, open session. We don't need to save that one. And in the example data folder, there's this synth example, and there's a synth underscore simple strontium spikes.io4 folder. So if we open that, we'll see that we don't have any files loaded, but we do have samples, which is a sign that this is synthetic data right from the outset. And when we go time series, what we can see here is we basically have some standards and we have some samples. And the samples, every second one of them has a little strontium spike that's supposed to represent an inclusion. And we can write processing templates that will avoid these inclusions. And the way that we do that is we create our selections based on criteria. So if we go to templates, and like I said, templates can have as many steps or as few steps as you like. In this template that we're going to look at here, it's actually going to not do any of the loading steps because we've already got our data loaded. So we're going to click on load, and we're going to click on the synth example, and there's this avoid spikes and link.template. And it just has two, excuse me, it has just two actions in it. So it's creating selections from channel data. And the way that we look at this is if we were to go to our tools, automate selections from channels tool again, and this shows us our data. Down here, we're going to look at strontium because I've already told you that's where our spikes are, but you might know this from your own experiments. And when I look at the strontium data, I can see that our good data, which I use in inverted commas, is all around about 60,000 counts. And then our spike is greater than about 70,000. So I could just put in, select everywhere where strontium is less than, let's say, 69,000 counts per second. And what it'll do is if I click those selections, you can see that it's selected the data up the edges of this just slightly. So we can put in a crop time there of about 0.5 for the start and the end, just so it doesn't climb up the edges a little bit. And now if we select these, The green parts are the parts that match our selections. But the point of this example is that if I've got it right for this selection here, because I'm working on a input channel, it's affected by baselines and it's affected by sensitivity drift. And if we zoom out our data completely, you can see that we're actually got about 30, well not about, we have exactly 30% decrease in sensitivity over the course of this experiment. I use experiment in inverted commas. The problem with that means that if the criteria that we use to get rid of this spike also gets rid of some valid data in our previous example when the sensitivity was higher, and you can see that by the time we get to our last spike, it's not getting rid of that spike at all. So the advice here is that you don't use the input channels at all. You don't try to avoid the spikes before you've calculated your output channels. So I've already gone ahead and calculated our ppm channels. So if we use instead strontium-88 underscore ppm, what that will do when we have a look at it is that it has been corrected for baselines and for sensitivity drift. And so if we use our criteria based on strontium-88 underscore ppm, we don't have to worry about that sensitivity drift anymore. So if I was to use a value, if we were to zoom in on one of these spikes again, where I said anything less than about, what's that, say about 83, and we're talking in parts per million now, 83? 83 seems high. What value did I put in here? 89. So if we put in 89 instead, same thing, it's still just climbing up the edges just a smidge, so we could put that down to say 1 second. And now you can see that we've avoided our spikes. And not only that, we've avoided them, we've selected all our good data for these, and we've also done it for all of our spikes. So we can put that criteria into our action here. So it's going to look at strontium ppm, and it's going to do these crop values here. But then what it'll do, so if we were to run that action, if we were now to look at our selection groups, so we have our SAMPs, which just selected, these are ones that I created earlier. We have this group that selects everything, and we have this one where it actually avoids the spikes. So if I zoom in on here, you can see that it's avoiding the spikes. So that's how you can avoid inclusions. But then that actually gives us 2 selections for the one sample. And so what we want to do there is we want to link these samples. And I'm not sure if we've talked, so link these selections. And I'm not sure if I've talked about selection linking in the past, but we can do that in templates by running a link selections action. So what this will do is we tell it what group we want to act on, which is this no spikes group, which is what I called this group here, no spikes. And it has these selections like this. And I say to it that any selections that are less than 20 seconds apart, I want you to link them together and treat them as one. So let's run that action. And now when we go to this, you can see that it's created a linked selection. And for those of you who haven't come across linked selections before, what a linked selection is if I go to zoom in a little, is that a linked selection has component selection. So it's got one component selection here and one here. And when it calculates the stats for this linked selection, which you can see in orange, it takes the data that's in this selection and the data here and treats them as a combined whole. And it gives the stats for that. And just so you can see what that looks like, if we were to look at our strontium ppm values for with spikes and for no spikes, and we hide our component selections, well, actually, there's not a huge difference. This is one with the spike, this is one without it, so it's just slightly lower. And the reason for that is that these are very short spikes and they're not very high in magnitude, so they don't really affect our results a whole lot. But that's just to show you how you can do that. Okay, so I guess the moral of that story was, if you're going to avoid spikes, do it on your output channels, because then they've been corrected. So I've mentioned this briefly, and I wish I had more time to discuss this, but one way to think about your experiments is that you can mark your samples as being either clearly okay because they pass certain criteria, and then you can create groups with selections that are in the maybe okay pile, and then you have another group that's in the no, this is definitely bad pile. And by doing that, you know that if they've passed tests that you've set for it based on criteria, then you don't really need to check those. You definitely should check them, but they require much less time. But by putting the ones that do need to be checked in a single group, it makes it much easier to look at them quickly, because you've already identified the ones that need to be inspected, maybe adjusted. So how do we do that? Well, there's a move selections action. And the way this works is you can choose on what basis you would move a selection from one group to another. And you can do that based on the uncertainty, whether that be the 2SC or 2RSC, 2SD or 2RSD. And you tell it which group to look in and which group you want to put them in. So this is a uranium lead example where I've said, look in my sample group, which is called DRO, and put all these suspect ones into a group called to check. And then I want you to move them where the final age, the final 638 age, has a 2 RSE of greater than 5. So where it has a little bit more uncertainty than normal, put them into this other group and we'll check them. I do have an example where we do that, but I'll skip over it just for time. But it's just an idea. It's plant in your head that you can set up your experiments this way. I mentioned that you can calculate your own channels, and as an example of that, which I won't run for sake of time, is we have an example here where we've calculated the silica gradient. And the reason why this could be really handy is because if you look at the gradient of a channel, it doesn't necessarily matter what the content is, just more where it's moving quite quickly. So for example, in our Gabros, we can have different contents for silicon in our plagioclase in our CPX, but where we have drill throughs, that gradient will be quite high. So here I've said, look at the change in silicon 29, smooth it, and I've put in a massive smoothing amount there, but then also look at the absolute, because we don't care if it's moving up or moving down. We just want to find all the areas where it's moving quickly, where it's changing quickly, and we want to avoid those areas there. So you could actually create a channel and then select based on where those values are low. And just to finish up, we'll just have a quick look at a uranium lead example. So we'll say session, new session, because we've already got files loaded here, samples loaded here. And we're just going to have to change the timestamp for this example. So this one, we just need to chop off the one of the hours. So we just click in here, and it should be DD capital M years 1H MMSS. We'll click save. Then in the templates, we have another uranium lead example. So in the example data folder, there's a uranium lead example. If we click on this uranium lead processing template and we click open, you'll see that it imports data, selects baselines, our secondary and primary reference materials. It runs the uranium lead DRS, the basic uranium lead DRS. It moves those selections, like I said, so you can try that out later on. Then it does a pause for us to go and check. But just as an example of running a Python script, this last step here we have is one of these run Python code steps that you can see here. And this is a little bit of code that Joe and I came up with. I came up with the idea, Joe did the actual coding, where it calculates the discordance, so the difference between the 638 age, and in this case, it's looking at the 735 age. And you can see that that's what's calculated there. So it creates a new channel called discordance. And then for each of the selections in the DRO group, our sample group, it then tries to optimize. It tries to select as much of the sample as it can, while also minimizing the amount of discordance. So if we just run that, it'll take, so the first part of it's quite quick. It's going to get to the pause step. Obviously, this is where we check our results, but we're not going to just here. So I'm going to click resume, and now it's running this select for minimum discordance action. And as I mentioned, it's taking a little while because for each selection, it's taking each selection, calculating the discordance, and it's then trying to extend that selection as far as it can before it becomes too discordant. So it is actually looking at every single data point in every single selection in that group. And I'm not saying this is what you should do with your data, not at all. I'm not saying that this is necessarily valid. It's just an example of something that you can do, a more advanced thing you can do with Python scripts. So if we were to look at our data and we were to look at, say, the final 638 age, and we've got our DRO group and we've got our optimized group. And it's very hard in this view to see the difference between them. But if we went to visual age and plotted up a live Concordia, if we're looking at our unoptimized group, you can see that it still has some discordance there. And our automatically optimized group is now plotting basically over our Concordia. As I said, not necessarily valid, but an idea, the germ of an idea perhaps. Okay, so just to finish up, I've shown you a couple of those shortcuts where you can right click on your actions. There's some other automation ideas that we didn't get a lot of time to talk about, but there's configuration files that you can run, where you can save things that you do repeatedly. So keep an eye out for those. They're normally just like a little folder button like up here. So if we had a certain configuration in this window that we liked, we could save it as a preset. Same thing with our QAQC. If we set up our settings here, actually that's a bad example, it doesn't have it. In the secondary check, if we set up all our samples with all our exceptions, etc., we can click on this button up here and we'll save the settings. So you don't have to keep doing that over and over again. Okay, so yeah, keep an eye out for that. All right, so to summarize, hopefully I've demonstrated that processing templates are quite flexible. You can do quite a lot of different things in them. Once you have them set up for your lab, they will do reproducible actions. You can build up more complex templates based on a series of simple actions. So you might start off simple just by creating selections, and then you add more complex things like moving selections based on criteria. And also, I should have mentioned at the start that template files are completely open. You can share them between your groups, you can publish them, you can pop them on the forum if you think that'll help everybody else. The idea was that we didn't want to make templates for everybody else to use. We wanted other people to be able to create templates based on their own ideas. So with that, I'd say thanks for sticking with me for an extra 50% of the time advertised. If you have any troubles with your templates, questions on the forum, posting there will let other people see the answers that we give. So it'll create a knowledge database. But yeah, otherwise, thanks to everyone for coming along. We already have great ideas for improving templates based on our interaction, and sometimes we get interaction after the webinars as well. So if you want to hit us up with some ideas, please feel free. Otherwise, we'll be presenting more webinars soon, and we look forward to catching up with you then. So thanks everyone, and I'll end it there.